look at two MOEAs in sort of detail. I'll describe two more, but it will be much more brief. And then we can try to look at some of the applications. So this is 2001, NSJ towards 2000, SPA2, it's called Strength Pareto Evolutionary Algorithm. And again, this is version 2, so there was SPA before. It's not really self-explanatory, but this strength means this algorithm assigns fitness of solution X based on the strength. So it doesn't really define strength in the title, but strength of X is dominators. And then we minimize on that fitness. So what we want to do is for each individual, so we want it to be dominated by weaker and weaker other solutions until it does not get dominated at all. And then at that point it has reached the final Pareto front. Okay? And then there is density function for niching. Niching is another word, another expression for achieving diversity. So you want to find niches in the Pareto front. If there is a large empty space between two solutions, then you want new solutions to appear and fill up that niche. Okay. Really, no other way to go through SPA2 other than going through some boring math. So they first defined what they call score, but I'm not sure why they didn't actually call it strength. So the score of solution I is the number of other solutions that I dominates. And really annoyingly, I think this paper is using that operator in opposite way from NSJ2, right? So when he's saying I is clearly greater than J, then it means I is dominating J. Forgive me, but I couldn't do anything about it. The paper's already been written. So the strength of S is the number of solutions that I dominates. Okay. PT means population, and then we have a separate archive. So this is where we store the best solutions that we have seen so far. And so we consider both the population and current archive to count the number of dominated solutions dominated by I. Okay? So in other words, score means number of solutions I dominates. Okay? And then we define what they call raw fitness. This will be a component of the entire fitness function, but so far it's just a part of it. So the raw fitness of I is the sum of the strength of J, and J is all the solutions that dominates I. So in other words, sum of its dominator's strength. So for each individual I, you first look at all the other solutions that's currently dominating me, and then add up their strength. So when do you get a non-dominated solution in terms of raw fitness? When I becomes 0. Which means there are no other solutions that's dominating you right now, okay? And then the other component is the density function. Ideally you want to look at the paper really, but we first define the sigma of K and I. From the solution I, this sigma Ki is distance to the nearest K neighbor in terms of some distance measure that you can define over the objective functions, your solution space. So immediately it brings the question, so it only sort of works if your objective is real values or continuous domain or whatever. If your objective is something that's discrete, then there will be questions about how you define this distance. But suppose it's continuous, so real numbers basically. And then sigma of Ki is based on that distance function, distance measure, you pick the K nearest neighbor, and then the density is sigma of Ki plus 1 over sigma of Ki plus 2. And then the kth neighbor, K, they suggest using this, which is square root of population size plus archive size. But I guess you can play with it. That's definitely parameter, not a given rule. So density becomes higher if sigma of ki is lower, meaning the kth neighbor is quite close to the current solution that you're looking at, right? So if the kth neighbor is really far away, which that means the density around the solution is low. So that gives you an idea about something similar to the crowding distance in NSJ2. And then finally, we define the fitness as the raw fitness that we described here. Who's dominating me plus how many other solutions are around me. And then we want to minimize that. So we want less and less solutions to dominate me, and also we want weaker solutions to dominate me, because gross fitness is some of the strength of each dominators. And then we want less and less solutions around me, because we want low density. So by minimizing this, we will push solutions to the perfect one. So here we have, NSJ2 had elitism, meaning that the best front always gets carried away, carried on to the next generation, but it didn't have a separate archive, whereas SPA2 has this concept of archive. So, okay, after we calculate fitness for the current population, how do we update the archive? Again, it's a bit ugly, but okay. The archive for the next generation, so P bar means archive, and T plus 1 means current generation T. Now we are looking at the next generation T plus I. All the solutions for which fitness is less than 1. How do we reach fitness of I less than 1? If you, so only explanation, if you remember the previous slides, I will not go back at this point. That means our the raw fitness is 0, and then only the density remains. That's the only way you can reach below 0. So it means it's this basically says out of the current population and current archive, we want all the non-dominated solutions. Density is not featuring at this point. Okay, and this will give you two cases. First, whatever we take out from the current generation and current archive, the size is smaller than our archive size. In that case, we can take them all, and then there are some space left. If that's the case, then we will fill the remaining space with solutions from PT. And I think we are supposed to, we can just sort them according to FI, and then pick the next that many solutions from the current population. That's easy. If, however, the updated archive is larger than our predetermined archive size, we now have to truncate the archive. The way we truncate archive is, let's see if I can remember this. We will truncate all the solutions in the next generation archive, such that this relation holds. There was a term for that, but what it means is, for all k, the density is the same, and for all there exists some k in the next archive that then some other number that smaller than k, there exists a solution that's within the density range. I'll give you visual explanation. So if that was our archive, right, then we will start deleting solutions by looking at what's the closest next solution is. So the one that has the smallest distance to the next neighbor gets deleted. So if that was your initial archive that needs to be truncated down to 5 solutions, then this is the first one that gets deleted because it's really sitting close to that other solution. And then second one, and then third one, and then at this point we get 1, 2, 3, 4, 5 in the archive. Does it make sense? As a brain teaser, I recommend you to go through the math again. Right? If you compare SPA2 to an SJ2, you can sort of see that why an SJ2 was such popular. I mean, this is somewhat a long-winded way of determining how to push solutions to the operator front. The convergence is determined by strength of your dominators, which is sort of not as intuitive as the non-dominated sorting in SJ2. And sort of naturally, it follows that an SJ2 really took off, whereas SPA2 features as an algorithm that you compare an SJ2, but I don't think anyone has really sort of took this as their main optimization tool in application areas. But it sort of shows you there are really many ways of reasoning about how to push solutions to convergence and how to define the partial order between solutions. Even more radical way is introduced by PSA2, PESA2. This is a sort of spatial approach for selecting solutions. I think this is a correct envelope somewhere. I think E stands for envelope. So what do I mean by spatial approach? It defines hyperboxes in the multidimensional search space. So we divide up the search space into equal-sized hyperboxes, and then your population will occupy certain boxes, right? And then each occupied hyperbox gets assigned a fitting space on the crowdedness. And then we will not select each individual solutions whenever we need to apply genetic operators, but we will instead select these boxes. And then actual individual solution is sampled randomly. And then again, we will maintain a non-dominated archive. So this is their argument. It's purely hypothetical, I mean, because it's very simplistic. But let's assume that we have 2 boxes in our search space. One of the boxes have 9 solutions in it, and the other one just 1. And then let's say we want to really choose one because that one solution is the most isolated. It's more valuable, right? Okay. Well, the author's argument is with NSJ2, we do not care about really hyperboxes. And if you allow selecting the same solution twice, which I think is a bit unfair, but that's the argument in the papers, then chance of selecting the most isolated solution is 1 minus 9 over 10 squared because we select twice, right? Therefore, it's 0.19. Therefore, chance of choosing the one of the most crowded solution is 0.81. So basically, everything else. So with about 80% probability, we will end up picking the crowded solution, which is not really ideal, right? With PESA2, authors argue that the chance of choosing the less crowded box is 1 minus 1 over 2 squared 2 because we are just choosing boxes, not individuals, right? And therefore, choosing the one of the more crowded solution it goes down a bit, 0.75. I mean, it's not the strongest arguments that you can make about your algorithm, I think, but there you are. Then finally, this is really quite recent, 2006. It's even more operational, and I mean, if I try to describe what it does, it's just another page full of pseudocodes. I'll just describe it in text. So what the algorithm is simply called 2-archive, and this is really the strength of it. So this algorithm looks quite similar to an SJ2, but it maintains 2 different archives, one for convergence and the other for diversity. If you find a new solution which is not dominated by both archives, and then the new solution dominates at least one solution in either archive, it goes into the convergence archive. So it pushed the boundary a bit. So we add it to the convergence archive. If a new solution is not dominated by both archives, so it hasn't really pushed the boundary, Oh, no, no. New solution is not dominated by both archives, but fails to dominate any solution in either archive. So it hasn't really invalidated any of the existing solutions in the archive, but then it added some other points in the front. Then it goes into the diversity archive. So a new solution goes into the convergence archive if it dominates one of the existing solutions. If it doesn't dominate existing solutions, but it's not dominated by existing solutions, then it has widened the front, so it goes to the diversity archive. And then whenever we reach the archive size limit, convergence archive is preserved, diversity archive is pruned based on crowding distance. It's quite simple, actually. So this is another way of reasoning about how to maintain your convergence and diversity. And this sort of operational level approach again works. And I know the authors, and he said the algorithm design was particularly focused on beating NSJ2, and I think they beat them both benchmarks. So yeah,
they beat them on.
So there are benchmark problems for multi-objective optimizations, and you can exactly measure how many solutions you find, how diverse your operator funds, etc.
But presumably this has more computational complexity.
Yeah, I think so. Yeah, I haven't calculated, but a bit more than NSJ2. These two checks, I think it consumes, at least double, I would say, because each check is n squared for comparing pairwise population size, and then each check involves m comparisons for m objectives. But then we are doing it twice, so one for checking with convergence archive and one for checking with diversity archive. So that's at least twice the NSJ2 effort, and then plus the truncation happens.
Plus, I had a question about the previous slide, because it seemed a bit of an arbitrary case.
It's only for the argument. It's not for actual running of the algorithms anyway. So yeah, if you're really curious, I can spill the beans. And it hasn't succeeded that much. I would say if your solutions get sort of reasonable coverage across all the hyperboxes, then I think this makes sense. But if it's, in many real-world problems, even when you think you have randomly initialized your population, the density sort of differs a lot. So what you think is random is often not random at all in terms of what sort of distribution of objectives they achieve in the solution space. And if you apply this to your problem and then most of the solutions goes into one or two boxes anyway, then I don't see this happening. I don't see this achieving a lot compared to something like SJ2. And also there's the random element, and what's the size of the hyperboxes that you need to define, so other parameters which are completely different from other algorithms. So that will feature a lot as well. So you can get as many hyperboxes as you want based on how you parameterize that space, and that will have an impact on the performance as well. Any other questions? One thing is, it is notoriously difficult to compare these algorithms in terms of precise complexity. Although there are people who do that. So there are some proofs, although it's way above my capability. If you fix some sort of simple enough problems and then fix a simple enough EA, even multi-objective one, you can actually mathematically prove that the runtime is at least, the worst case runtime is that complexity. There are people who does that theoretical approach to these types of algorithms, but in general it's very hard, and any practical problems will escape that sort of attack. You cannot really say which one is better than the other. Therefore, everyone's doing empirical evaluation. So you either run it against benchmark, or if you care for particular problems, then you apply at least 2-3 algorithms and say, okay, this seems to be doing better than the other, but actually reasoning about why this algorithm does better than the other in terms of this particular solving this particular problem, it's very hard. So if you want to work with evaluating multi-objective algorithms, then you might as well get very good with statistics too. So that's usually only reference usually. So you run lots of things and then statistically argue that this seems to be doing it a bit quicker than the other, that sort of thing. All right, if you are not yet bored, now I'll explain a bit about what our center does. It has still a lot to do with what we just covered today, and also what Mark did earlier in this course. So basically, to tell you that what you have learned throughout this course is not just thought experiments. There are people who are actually using it. So no, really, real value. Well, we like to say that engineering is all about fine-tuning trade-offs. But what's funny is, I don't know your backgrounds that much. So has any of you worked as a developer in commercial sector? No? You chose machine learning course purely for academic interest, or for its applications later. Okay. Is software engineering I mean, is it close to building bridges or developing new chemical compounds? What do you think? Searching for new materials, is it close to writing new software? You're shaking. There is the traditional sort of purist view that software is still applied mathematics, and you should prove its correctness, and it will not wear out. Material doesn't change, so once you write it perfectly, then it will always remain perfect. Therefore, it's not really engineering, which I disagree a bit. So the SE group in UCL has this big claim that it's really similar to other engineering as well, and therefore it's all about trade-offs. So what we like to say often is, okay, if you are writing compiler, how much speed you get out of compiler optimization versus how large the end result binary is. That's trade-off. It may not be that smooth and continuous, but there is still trade-off of some kind. The time it takes to execute your tests versus how confident you are in the software quality. That's again a trade-off. Again, not very smooth maybe, but still. And other things. So our group is one of the main expertise really, is about applying optimizations to this sort of problems in software development. So it's called search-based software engineering. So instead of optimization, we opted the word search. So we want to reformulate software engineering problems into optimization. And we work with all kinds of software lifecycle. Although, for some reason, testing has been very big. We will see a little bit about why. And really, UCL is quite well leading in that domain. We actually claimed and introduced the concept. So, there is a reference page at the end of the slides, but there's a nice paper, really a tutorial that you can read if you are interested in the application area. There are papers coming out more and more each year. But it's not really different from what you have learned about genetic algorithms. So it still takes the same ingredients, fitness function, define your real-world problem, and then try to express the property you want in mathematical terms. You can either look at existing metrics, because there are tons of metrics in software engineering, or you can try to mathematically describe the qualitative properties that you want. But I said qualitative properties, but in terms of writing the function, it needs to be quantitative, of course. Representation, so you need to have a solution representation. So sometimes you inherit the representation from the problem, or you can get creative. There are problems where you need to come up with quite radical representations. And then optimization algorithm. GA is very popular. We assume that because it sounds quite sexy, you know, it looks attractive. Whereas if you say something like hill climbing, a local search, it sounds a bit dull. But then, you know, you should think about others as well, because in this context we are not really interested in GA, but we are interested in solving problems. And if other algorithms does better job, then why not? So I'll go through a bit of case studies. Test suite minimization. Does the name mean anything? Is anyone familiar with the term regression test? So what software developers usually do is they write lots of test cases, and every time you modify your source code, you run the same set of tests over and over, okay? And then in the next version, you add a few more tests because you have added more code, etc. And as the version goes up, your test suite gets larger and larger and larger. And if you are really serious commercial software outfit, then eventually that's what we call regression test suite, the one that you keep and check against all the previous faults or all the version history. And then your regression test suite gets too large. You cannot really run it. We're not really talking about hours, but we are talking about days or weeks to run the entire thing against all the environments that you care about. So there are people who came up with this idea that there must be some redundant test cases. So if you have written your regression test suite over a long time, then there has to be 2 or more test cases which ends up doing the same thing. Therefore, you can leave some of them out. So the proposed solution is to minimize or reduce the test suite by removing all the redundant tests. So this is really the classical set cover problem, but with optimization twist. So what's a set cover? So these are things you want to cover, basically. And then you have different entities that cover different parts of this set, right? This is a full cover, right? If you take these 3 covers, then we have achieved all the was the last one really necessary? No, because the first circle, the solid line, already covered all 3, right? So if you, that's redundant, so it can go away. So if you think about these circles as the test requirements, test goals, R0, R1, R2, R3, and R4 needs to be tested. And then these circles are your test cases. Every time you execute one, the circled requirements are met. Okay? And then we had 4 test cases, and then this one was redundant, so we dropped it. So that process is minimization, and it is actually a classical set cover as well. So usually we start with this type of matrix. So these are your tests. These are the, well, I say things to tickle. So by running these tests, we want to check that, okay, R0 checked, R1 checked, etc. So if it's checked, we will write down 1. If it's not checked, we will write down 0. So that's your tester-testee sort of relationship. And then you can also think about the time it takes to run this thing. So T0 takes maybe 2 minutes, T1 3 minutes, T2 7 minutes, etc. Okay. So now the question is, if I have, say, 5 minutes, what's the best testing I can do? Okay, I cannot run everything, which will take 15 minutes. I only have 5 minutes. What's the best testing I can do? So based on this data set, we want to answer that question. So yeah, it's a set cover. The exact solution is NP-complete, although there is a quite good approximation, really. But then if you want to do multi-objective optimization, then there's no real good approximation. So what we want to answer is, what we want to achieve is to select a subset of tests given those kinds of table that minimizes the cost, the time it takes to run, and then maximizes the coverage, which is how many things we can tick off. And then possibly maximize other desirable things. So if we know that which test has detected previous faults in the past, then we want to include those as well because they might be good tests, better tests than the others. And then that paper I had was based on NSJ2. So a case of this algorithm actually doing some real work. And then there was collaboration between our group and Google. And this is to give you some glimpse into how many tests is being run and why this problem is real. So this was back in 2010, and I think they do probably more than this, but they have this fully automated testing framework that runs 120 million tests each day. So it's continuously running, and the test invocations goes up to 120 million tests. So, I mean, if you can reduce this number even by a little bit, you would at least save electricity, and, which means money for them, and for us it's better environment and everything. And yeah.
Sorry, I just had a question, because from that algorithm that you described, it seemed like the implicit assumption is that the redundancy is distributed more towards tests that run for a longer time because you're limiting to constrained time. But you have no idea beyond that which tests are actually redundant. But the assumption is that those with a longer time have a disproportionate amount of redundancy. But then under SGA2, you're looking for diversity, and so you might be eliminating.
No, I wasn't implying that the test that takes longer is more redundant. The redundancy is defined against what you want to tick off, basically. So if everything has been ticked off, and then some other test ticks off the same thing, then then it's redundant, regardless of how long it takes.
Okay.
So we'll see how NSJ2 formulation of this problem works in a few slides later.
So in that table, you weren't just looking to maximize the number of tests carried out.
No. I was. What we want to maximize is number of things that has been ticked off by choosing a subset of the tests, while using the minimum time possible. So it's a trade-off between how many things you can tick off versus how long it takes to tick them off.
Exactly.
Yeah.
That's exactly what I'm saying. But
yeah.
it's beyond that. The redundancy isn't explicit. It's an implicit assumption that it's distributed. Maybe I'll take a closer look.
Okay.
And,
well, yeah, we can discuss it offline. And also, what the minimization means to their context is the developer needs to get early feedback. So if you, instead of running 1,000 tests for the code you just submitted, if you can run only 100 and still see that something has been broken, then it's much easier for them to go back and fix them because you do not have to wait 10 times longer. Okay? So right, so this is what the solution looked like in their case. So this is CL means code list, I think. So this is a 1 unit of code submission to the repository, anonymized. And then we applied NSJ2 to 3 objectives really, but let's focus on 2 first. So just look at the circles, okay? On the x-axis, we are measuring the CPU time in seconds, of how long it took to execute the particular subset. Okay? And on the y-axis, we are measuring how many things we have picked. Oh, okay. Cone coverage, but that's too much detail. Just think of it as how many things we have picked up. Okay? And then the circles, each circle represents one particular subset that you can choose out of all the available tests for this code submission. Okay? So the trade-off we are seeing has this shape, right? Usually it is, I mean, this is the shape you see between time and coverage. So as you run more and more tests, you consume more and more CPU time. But then because certain tests will overlap in terms of what they take off, the increase you get along the coverage, the y-axis, decreases as you add more and more tests. That's why we get sort of this shape, right? So that's the trade-off between CPU time and coverage in this particular case. And it's, I mean, it is our aim is to look at this trade-off. And then what we added in is the third objective, which is to see for each of the tests, we knew how many faults it has detected in the past 3 days. So we counted that, and then we made that as an additional objective. So that's why we are seeing this multiple strand of circles, right? You know, there are 3-4 lines of circles falling off. And that's because we have squished another dimension onto the screen. And basically, if we want to execute the test that fails, that has failed in the past, they actually consume more CPU time. So this is the rightmost line is one that includes the failing test in the past. And we have actually checked it against the current run. And surprise, it's the rightmost circles that actually fails, which is painted with red. So what this shows is, one, the trade-off between the CPU time and coverage, and then two, it is actually worth running the more expensive test because they have failed in the past, and then they are actually catching faults in the current code submission. Oh, sorry, I was not NSJ2, it was to archive. So does that answer you? I mean, does it clarify your question a bit? So yeah. So each of the circles that sits above something else is ticking off some new elements that haven't been ticked off by this. So in the end, what we wanted to achieve was some tools like this. So if you invoke it, then it will tell you whatever you change in this current directory will affect that many tests and that many libraries, and therefore you want to, and then it will affect these products. It's just writing nonsense there. And then you can recommend list of tests that will finish under 20 minutes so that you can get some early feedback before you actually submit the code. So we are using optimization to custom tailor sets of tests that can be executed within certain time limit so that developer can get early signal in terms of what will fail and what will not. The other experiment we have done with this is to run to convert the fitness evaluation for that set cover into matrix multiplication. I will not go into the details, but it turns out that evaluating whole population for that problem is actually multiplying two matrices. And then matrix multiplication is really ideal application for using the graphics card because it's very parallel. Each matrix element in the end result is a separate thread, therefore you can massively parallelize it. So here we are running an SJ2, SPA2A, and 2 archive, and then basically the highest lines are GPU buttons, graphics card buttons, and for all algorithms, NSJ2, SPA2, and 2 archive, I think we are achieving much more speed up compared to when you run the entire thing on CPU. And what's really interesting is this is, as you go to the right side, the problems are getting bigger and bigger, and the speed up is getting larger, higher and higher as well. So the bigger the problem is, the faster we are getting by using the graphics card, which is quite nice. So one really nice case was, this was a large smoke test scenario from IBM middleware, and then if we ran NSJ2 on the data set, it used to take 1 hour and 20 minutes or something. And then with graphics card, it was 2 minutes, which is 6 seconds or something. So interesting things. So if you want to, this is a quite interesting area. All the GAs are inherently a bit parallel because each solution requires its own fitness evaluation, which is independent from others, right? So it's a quite good application area for GPG, and people are working on it quite hard.
Was that using the standard graphics card in the Mac?
Yeah, this was fairly old iMac 27 inch, but from 2009. It's not nothing fancy. I think you can do better. I didn't really try that hard to screen that, but simply writing the matrix multiplication kernel for that looks quite well. Right. This has something to do with a little bit of theory that we went through. Test data generation. So if you have written some software, and now you want test data to test it. So, but in particular, what we are looking at in this application is, okay, you want a input that will take you to the line 25 of your source code, right? And there are conditions and loops and everything. So you're not quite sure which input will actually execute that line. So can you automate them? The goal to automatically generate a test input that will execute a target structural element, so a statement or a branch. Okay. So we. Our representation here, the genotype and phenotype is the same. Basically, it's just your test input. So it's either a set of numbers or strings or anything else. It can even be complex like trees or lists, but it's more advanced stuff. Here we can restrict ourselves to numbers. And then for fitness, we define two things. One, what we call approximation level, and two, branch distance. Approximation level. Let's say this is your code and you want to execute this print statement. Okay? So x needs to be equal to 1 and y needs to be less than 0. Approximation level is number of critical branches that are between the target and where we go wrong, basically. So bear with me 1 minute. Let's see if we try the test input x0 and y0, then where do we go wrong? Here, right? Because we want to go down that path, but because x is 0, we go that path. So, and then that's where we go wrong. That's our target branch. So there is one other critical branch which sits between where we go wrong and our target. So that's why we say approximation level 1 for that input. Whereas if we try x equals 1 and y equals 1, then we go down that path, so that's passed. That's okay. But here we again go down this branch, so we miss it, right? But we are here and our target is here and there is no other branch between these two. So that's approximation level 0. What we are measuring essentially is how close we are to the target, right? And how many more hurdles we need to jump through before we reach our target. So here we had to reach, we had to go through another one, whereas if we are going down there, then there's nothing else between us and our target. So that's approximation level. And then branch distance is, so approximation level was within this graph, how far are we to the target node. Branch distance is when we are actually looking at a particular branch, how close are we to choosing the branch that we want to choose. Doesn't make any sense. When logicians will poke their eyes because there's no concept of how close it is to the being true, but it's either true or false, but we can't measure it. So if your predicate says A should be equal to B, then you can measure how close we are to by minimizing the absolute value of A minus B, right? When that becomes 0, we have reached our target and made the predicate true. And then you can also define if A is less than B is our predicate, then we define the branch distance to 0 if A is less than B, or A minus B plus 1 otherwise. And again, minimizing this part will bring us to A being less than B in general. Okay? So if we are here and our current test input is x equals 0 and y equals 3, the branch distance is 1, because currently x is 0, x needs to be 1, so therefore there's 1 difference of 1 from 0 between current value of x and going down that path. And if x equals 1 and y equals minus 1, then we go down to here, and to the target node we have this branch, and branch distance is actually 0 because y is less than 0. So now if we combine approximation, this is how we define the branch distance for all the predicate types. So if you combine approximation level and branch distance and minimize it and try out various input values, then you can eventually make the whole fitness function 0, and then you can execute that particular target. That's how you usually automatically generate test input using GAs or other optimization methods. One optimization method that is quite popular with test data generation is alternating variable method, AVM. It's a variant of local search. We start with a random solution, a single solution. This is not GA, so no population. We start with a random solution and make a small explorative move. So tweak your current solution just a little bit and see if it makes the fitness any better. If it improves the fitness, then we double the data. So accelerate to this direction if it's keep getting better until it fails to improve, and then we start making the same moves but with next variables. So that's why we call it alternating variable method, and it is quite effective. So the paper I mentioned in the title of this subsection was comparing this method against GA. What about GA? Is it supposed to work as well, or does it have hard time? So the authors compared lots and lots of programs, source code, and applied the alternating variable method and GAs as well. And let's see, this is covered, the branches that can be covered by AVM or GA both. So lots of branches can be covered by anything. These cannot be covered, uncovered, or infeasible. The black one is covered by random only, which is quite interesting. In random methods, covering something and everything else fails, that's a bit weird. And then if we look into the detailed view of this small lot, that's covered by GA only, that's covered by alternating variable method only, that's covered by everything. So this tiny bit is the branches that only GA can cover. So what's happening there? I think you have went through the schema theory of it, right? No? Royal Road? Does it ring a bell? Oh, come on, it hasn't been that long before. So yeah, that's the Mitchell et al. The figure taken from their paper. So Royal Road property is essentially it's describing the building blocks in GA, right? So if you can combine small bits of good parts of solutions into larger and larger chunk, eventually you can reach the solution. That's essentially the intuitive description of the Royal Road property. And where did the GA achieve its success? It's where there is a very clear building blocks. For example, this is one of the source code that they evaluated, and for this genetic algorithm did really well. And what do you think this function does? It's checking ISBN. So if you want to check this source code, then you need to give ISBN number as an input, right? And ISBN has strict rules about which digit can be what, right? So if your solution has partial digits correctly, then that's your building block. And if they accumulate, and at some point it will all click and get you a correct ISBN, then that's when you cover the entire source code, because now it has a valid ISBN. So it's quite hard for the local search to achieve correct ISBN, whereas for GAs, it's all about building blocks. And thanks to the schema theory, GA does quite well to test this particular source code. So this is not just applying GA, but sort of explain why it works and why it doesn't, using the theories of genetic algorithms, although there are not that much theory behind GA. There are open source, well, I say open source, some research tools that are available, so if you want to play with it. Austin is more local search, I think, but Evolutionary is totally GA. And this one does C, that one does Java, so if you're interested, you can look at it. I'll make the last bit short and we can just have 2 hours, is that okay? This is my last section. So, automated bug fixing. That was in the biggest software engineering conference, ICSE in 2009, and it sort of sent many people into shock because what they claimed was, okay, give us a fault and we will just fix it correctly using genetic programming. And you can see why people were surprised. It made quite a stir. But what's even more surprising is now we are 3 years down the road and it's sort of now accepted. Everyone says, yeah, okay. So now we have to do even more than this. Anyway. Has anyone used Zoom? I think it's officially discontinued now, is it? No.
But Microsoft.
Yeah. Do you remember the bug?
No.
2008, I think. January 2000. 1st of January 2008. All the Zoom players became non-responsive. The system firmware basically went into infinite loop because of this bug. Can you tell me what this does? It marks the end, was it end or beginning over a leap year, and there is a condition where this goes into infinite loop, basically. This, I mean, it tells you how complex the issue of bug fixing is, because if you look on the internet, there is lots of theory about what is exactly wrong with this code and what's the best way to fix this. No one has a definite answer yet, so everyone has his opinion.
Is it that it gets stuck at 366 days? It's not greater. It can go, if it's got 366 days, it moves in, but then it can't move into this the iteration below it.
Yeah. So for this for the formula to escape this, I think they had to wait 24 hours so that the bait actually goes one more and then it escapes the first batch of bait. So you have done GP now. So back in 2009, the question the authors threw in was, can we use GP to fix faults? And the authors made the following assumptions. We have positive and negative test cases. So we have at least one test input that goes through the faulty code, but it passes, right? So it doesn't reveal the fault. And then we have negative test case, which will go through the faulty code and actually it crashes or does wrong things. So we know when it goes wrong and we know when it isn't. Okay? Still quite hard. So how do you evolve large-scale programs? The most common attack against GP is, but you can only evolve toys. It doesn't really evolve a big complex programs. That's one attack. So there is the question of scalability about this work. Correctness. How do you make sure that the fix is correct? I think this is still open. So there are people who will not believe that. Okay, it's a patch that will sort of save you for the day or immediate future, but eventually human will have to look at it. But we do not. I do not think that sort of detracts from the value of this work. I mean, even if it's meant for keeping alive for another 24 hours so that human can have a look into it, why not? And finally, GP has the blog, the the famous GP bloat. So how do we get rid of it while preserving the essence of the evolved fix? So even if we evolve a fix, if it's 200 lines long, it's not really good. But then if we want to reduce it and get rid of the bloat, how do we make sure that the reduced version is still a fix? These are all sort of technical challenges. So what did they do for the scalability? Instead of ramping to initialize a solution, they use partial clones of the original program. This was quite clever, and after them, I think lots of people are doing this if they want to apply GP for real programs. So the assumption is, even if the program is faulty, even if the Zoom bug is actually a bug, it is almost there. It's probably 1 or 2 lines missing, or something misplaced a little bit. So assumption is the original program is quite close to the correct program. Therefore, we will take the original programs, or at least partial clones of it, as our population. We can even argue that solution is probably somewhere in the program as well, right? Think about things like null check. You have missed checking null pointers at some point, but surely there are other parts of the program where you do check. And then the only fix that you need to do is to copy that null check from some other parts into that. So GP can manage that. Also, they do some software engineering thing, so they will weight program paths so that the GP only focuses on the path that leads to the fault. It will not touch everywhere. It will try to focus on the faulty paths. Correctness. Well, they are being honest. The fix is only as good as the test, because we will evolve the GP patch using the positive negative fix as well. So when they pass all the tests, they will say, okay, this is the fix. Therefore, if the test is crap, then your fix is crap. But it's sort of given. Bloat, this is probably not familiar to you, but there is something called delta level, which is somewhat like binary search. So once you have this many fixes, then you try to do binary search, and each time basically you want to shed half of the code and see if it still works. If it doesn't, then reduce and smaller half, until you get to the minimum. This is what they looked at. But this is 2009 paper. After that, they have looked at much larger programs. So they have now processed things like the entire Python interpreter, and it's millions of lines of code. But back in 2009, this was still quite large. So the biggest one is, in terms of lines of code, just over 20,000 Tetris game, and there was a stack buffer exploit. How long did it take to fix that? 11 seconds. The hardest one was this HTTP daemon. Initially, without some optimization, it took 500 seconds, but with some optimization, it takes just over 1 minute. The recent work from the same guys actually ran the entire thing on Amazon cloud, and instead of reporting numbers, they reported price. So they fed in about 105 bugs, I think, and automatically fixed 55 of them. And on average, it costed them about $7 a code patch. So again, that was a quite interesting paper. They had the numbers in the title. So, yeah. Maybe I should update it with what I'm doing as well. So there are lots and lots of other applications. There are people who are doing genetic algorithm-based refactoring. So how do you refactor your source code to get better metrics out of it, so less coupling and more cohesion and that sort of thing. As long as you can measure those metrics automatically, you can let GA to shift around your code until the metrics improve, and that's how you do automated code refactoring. Requirements prioritization. So if you have lots of requirements and want to distribute your resources fairly or based on how much expected revenue you can get, according to all kinds of criteria, you can do optimization. Project scheduling and team building. So you have large chunk of project, you want to divide teams, assign work packages, etc. That's also being done with GA. Identifying desirable game character behavior. There was a paper about what was it? Super Awesome Fighter 4000 something from University of York. Basically, what they did was to use GP to evolve how a computer player would play a fighting game. And if you fight against it for some time, it will sort of get trained and evolve its behavior so it will not get beaten that much. So, GAs and optimization in general. You would be surprised if you look outside this course. They are picked up and used by all kinds of engineering domains. So the Bartlett Design School in UCL, the architecture school, I think they are quite heavily into optimization as well. So they do things from material to large structure using GAs, for example. And every other engineering domain, it's quite peculiar that software engineers are sort of the last to the game, but we are advocating that it has a practical application in software engineering as well. It takes the usual ingredients, and I think it's mature. And since you are on the sort of computational / optimization side rather than software engineering side, we are always sort of welcoming expertise on the computational side of things if you want to get involved. So I think I will be advertising a project at some point if you are interested. So I'm sort of left field compared to your usual projects, but then again, if you want to get something, I hate to say practical, but if you are curious, then doors open. These are the papers that were introduced today. The first 4 is really about the 4 algorithms. They're not that hard to read. It's just a detailed description of how they achieve convergence and diversity. I think the last 2 is actually quite short. This is a proper. How many pages is it? 9 pages. Yeah, they are not that hard to read. You should be able to find them if you Google from UCL network. And then the final one is a tutorial about search-based software engineering. So it tells you, what the idea is and how you would approach the actual practical application of GAs or other optimizations in terms of software engineering problems. That's it. Hope you found it interesting. I'm afraid I have no idea what Marx has in mind in terms of examination. May not teach that heavily because he is actually looked at it. So focus on the other things first. But and I'll email the slides to Marx so that you can download it from the website. Any questions? All right. If possible, I'll be at the project day, so you'll get to hear about it more. Okay. That's it, really. Thank you, guys.